As with everything, the method starts with the slope formula. So we're going to start with the slope equals. So I'm going to do my y2 and y1 off of here. And we're actually, I mean, you'll see how this works. I'm going to say that the slope is, I'm not going to use the 27 and the 3 because I want to keep this general for to be used for any function. So I'll just call this x1 and f of x1. So I'm going to have my slope be f of x1 minus 0. So I'm using this as the y2 and this is the y1. So, but you don't have to worry about that. Then down here, I want the x's, so x1 minus x2. Right, so you could also think that this is f of x1 minus f of x2 over x1 minus x2, which of course would be equal to f of x2 minus f of x1 over x2 minus x1, which would reverse the order or change the designations of the subscripts, however you want to look at it. All right, now that slope though, all right, is the slope of the tangent at this point x1. So that slope is f prime of x1. And this is not an approximation. The x2 is the approximation, all right? But the relationship among these terms is exact. There's not an approximation here. This is the exact slope between these 2 points that lie on this tangent line. All right, and then so f of x1 prime equals, we can simplify our top to just f of x1 over x1 minus x2. And then we can rewrite this as f prime of x1 times x1 minus x2 equals f of x1. And so now our job is to solve for x2, because what we really want is a method that generates x2 once we know what x1 was. All right, so we're going to solve this for x2. There are different ways you could do it. I'm going to distribute the f prime. So we have f prime of x1 times x1 minus f prime of x1 times x2, and that equals f of x1. All right, and then we're solving for x2, so we're going to put this term on the other side. So we're going to have negative f prime of x1 times x2 equals f of x1 minus f prime, of, which one am I moving? I'm moving this one, f prime of x1 times x1. All right, and then we just got to divide by negative f prime of x1. So then we have x2 equals f of x1 minus f prime of x1 over negative f prime of x1. Yeah, and then we're just going to rewrite this a little bit. So we have our x2 is going to equal. So when because I have this minus sign in the top in the numerator, I can separate this into 2 separate expressions, and I'm going to put this one first and reduce it. So the negative f prime of x1, the negative f prime of x1, we're going to cancel it in this term and just have x1 left. And then we're going to put this term next, so I'm going to have minus because it's a positive divided by negative, and then I just have f of x1 over f prime of x1. Okay, so this is the derivation of the method. This is the engine of the method. So this is what we do, how we do Newton's method right here. All right, so we can also then, we can generalize this, because if I then get my x2 and say, okay, now I'm going to have this x2 be my new x1, and then I'm going to find an x3. So I could continue this process and make multiple estimates. So the way we can write that is, what we're really saying is that the next x, the x sub n plus 1, is equal to the x that you have now, which is f of x sub n, minus f of x sub n over f prime of x sub n. And so this is how you're normally going to see it written. So all we're doing is replacing the 2 with n plus 1, so saying that we can keep doing this process. And because we can apply that same process again and again, repeatedly working toward better and better estimates, this is called an iterative method. And there are several iterative methods in numerical analysis. And this is your first one. So it's a process that you do again and again to get better and better estimates. So we will apply this to our particular equation in the next video.